So in the previous class, we have seen the basics of floating fixed point numbers. So basically the number systems are represented in two different types. So one is fixed point, another one is floating point. So in the fixed point numbers, we have seen different fixed point numbers, and with respect to that, fixed point numbers are basically like unsigned and signed. So in signed, we have seen three different types, and after that, we have seen the operations on fixed point numbers. So how we will be doing the addition, subtraction, multiplication, and now in today's class, we will see how we can do the division. So in the case of multiplication, we have seen different algorithms. So first one is the basic algorithm for positive numbers. The next one is the algorithm that is basically used for multiplication with the help of uh, the algorithm called Booth's multiplier, basically. So this can be used for both positive and negative numbers. So in Booth's algorithm, basically we have seen like how we can multiply the positive numbers, or even we can consider the case of negative numbers also. In case of like 7 and multiplied by -7, we can do with the help of Booth's algorithm. Next, we will see the division. So basically in division, so if we consider the multiplication, in multiplication, basically we were doing like if we are going to multiply a number with another number. So in multiplication, we were doing the addition and then shifting. Similar approach we can do for the division also is like suppose we are dividing 7 by 2. When we are dividing 7 by 2, so for division, what we can do is we can multiply, we can just subtract this 2 from 7, okay, and then shifting this bits of 7 in terms of like if it is 7, in case of 4 bits, it is like that, and 2 is like this. So we need to subtract this 2 from the 7. So we will be considering the different bits of 7. So starting with this one, so the 0 is there, so we cannot subtract 2 from 0. So we will be shifting it further. We will be considering now these 2 bits. So now we will be subtracting this from 0, 1. So again we cannot subtract. So we will be considering this 3 bits. And now we can subtract, and then after subtracting whatever the remainder is there, and then again we will be shifting. So this approach we will be doing for making the division. So how many times we should be shifting and subtracting is basically depends on the number of bits available, basically the number of bits available. So if it is 4 bit are available in the divisor and dividend, we should be considering the 4 times shifting. If for consideration, suppose we are having 6-bit numbers, this number is divided by this number, this is the dividend, and this is divisor. So we will be subtracting this divisor from the numbers here. So first of all, we will be starting with like we will be considering the first digit. So once we go with subtraction of this number from the first digit, like if we want to subtract this number from 0, 0, 1, we cannot subtract. So what we do is we will be shifting this number by 1 bit. So we will be shifting it. So after shifting, we will be considering like 1, 1 is there. And once it is not divisible, we should be considering as 0 as the quotient in that case. Okay. So here again, we will be subtracting this number from shifted this one. So once we will be shifting it, it is 0, 0, 0, 0, 1, 1. So again, this 0, 0, 0, 0, 1, 1, 1 cannot be subtracted from here. So again, we should be going for like the quotient we can consider here. The quotient is will be coming out this one, and then we will be shifting again. So like that, once we keep on shifting, we can get like once we have obtained 1100, 1100 is there, then it can be subtracted. This number can be subtracted now. This one is less than this one. So now it is able to subtract. So once we subtract it, the remaining will be this value. So after subtraction, once we are able to subtract 1 times, we will be making the quotient as 0, 0, 0, and then 1 we will be putting. And again, we will be shifting this one. After shifting, again, we will be checking whether we can subtract this number or not. And similarly, once we are able to subtract, we will be putting one extra one here. So that will be final after doing 6 times operation. This operation, because 6-bit operation is 6-bit numbers are there. So we'll be doing this subtraction and shifting. Either we will be doing this shifting only, or we will be doing the subtraction and shifting. So after doing the 6 iterations, we will be getting the answer like, so whatever will be the remaining, that will be the remainder, and how many times we are able to divide it, or how many times we are able to subtract it, that will be the quotient one. So the answer will be this will be the quotient, and this will be the remainder. So similar approach we will be going to take in case of algorithm point of view. Okay, so here basically we are going to see an algorithm only for positive numbers, or unsigned numbers are there, then only we should be using this. So basically in case of unsigned numbers, we are in division algorithm, we will be just seeing the concept of only the unsigned numbers. So in case of signed numbers, it is more complex, so that we have not considered into this. Basically, this is also not in your syllabus, you can consider that. So in case of positive numbers only, we will be going through 2 different algorithms. So one algorithm is called restoring algorithm for division. Another one is called non-restoring. So we'll see what is algorithm that is restoring and non-restoring. So basically, whenever we are going to do the division, it should be like the starting is like we are going to have, so whatever the dividend and divisors are there, that will be considered as 2 into n. So n is the number of bits for one divisor or a dividend. So 2n number of bits will be required, and the output will be also be of 2n results. So like 6-bit divisor was there and dividend was 6-bit. So after performing the division, we are getting the quotient q, that is of 6-bit, and another one is the remainder, that is also of 6-bit. So total we need 2 into 6, that is 12 bits to store the final value, final result. So similarly, n-bit numbers are there, then the result will be of 2n bits. Here the result will be stored or expressed in 2n bits and loaded into. So similar to the previous multiplication algorithm that we have seen, here the results will be stored into A and Q registers. So here at the initial point, we will be once we are going to start the algorithm, we should be considering an A register. A will be a like accumulator register, but register basically initial value will be 0. M will be another register, that will be the divisor. Q will be another register, that will be storing the dividend. So divisor is stored into M, Q, that is dividend, is stored into Q register, and count value is initialized with n value. So that n value will be equals to the number of bits available into divisor or dividend. So divisor and dividend will be having the same number of bits, that is called n number of bits, and similar n number of bits should be there into A. So all this will be of n bit registers basically. So once we have an initialized, we should be proceeding with the algorithm. So before that, we can just come here from like, so here once we are going to shift, and then we are subtracting accumulator minus the m value. So divisor we are subtracting from the A value, accumulator value we are subtracting. Okay, and then we will be checking the bits of assigned bit of accumulator. So once after subtraction, if the signed bit of the accumulator content is like a negative, or you can consider of A that is stored into A register is less than 0, means it is a negative number. In that case, if it is correct, then we should be going to make like Q0 bits will be make 0, and we should be doing A plus M. So initially you can just say, once we are subtracting A minus M, and now again we are doing A plus M. So initially we have subtracted M from A, but now we are adding M from A. So we are basically restoring A register. So here we are going to restore the A register. Basically, we are going to restore A register. So once we are using the concept of restoring, then this algorithm is called basically the restoring algorithm for division. So this algorithm that is shown here is basically the restoring type of algorithm, because we are restoring. First of all, we are subtracting the A, subtracting M from the A, and then again we are adding M to A. That means we are restoring the accumulator content. So this is called restoring type of algorithm. So it's another approach to perform the division is like here. This is the second approach. Okay. So this approach that is there, that is called a restoring algorithm. But in case of non-restoring, we will be removing the step like A minus M. After performing A minus M, we are going to store the result into A. So we are removing this part, and also we are replacing the sign of, we are checking the sign of the accumulator content. So we will be replacing this. We will be directly doing A less than M. If we are doing the A less than M or not. If it is yes, then we will be making Qn bits as equals to 0. If no, then we will be doing this one, this operation. So if we are going to make this type of modification into this algorithm, then we will not be able to use the restore algorithm. So we are, once we are not able to use the restore algorithm, that will be considered as the non-restoring. So this part we will see later. So basically we will be going with the first, that is restoring algorithm, and then we will see the non-restoring algorithm. So here once the operation is completed, at the end the quotient value will be stored into Q register, and remainder value will be stored into accumulator register. So we will just proceed with an example. So suppose we are able to divide 7 by 3. So once we are going to divide 7 by 3, so 7 will be equivalent to, so we are considering the 4-bit representation. So here 0, 1, 1, 1 will be the binary representation of 7, that is in decimal. Similarly, 3 in decimal. So its binary equivalent is this one, 0, 0, 1, 1. Okay. So now we will be making the initial arrangement. So initially the accumulator content is coming out to be 0. So here the accumulator is initialized to 0, 0, 0. That will be also a 4-bit. And also here we need to make the value like count. So count value will be initially initialized to 4 value. So because number of bits in divisor and dividend is 4. So M value will be stored by divisor. So divisor is 3. So 3 is 0, 0, 1, 1. And Q is dividend. So Q is 0, 1, 1, 1. So this is 7. So once we have initialized, we should be starting with the flow of this division algorithm. So the first step is we need to shift the AQ content. So shift left the AQ content. So the first we will be going to make is we are going to shift the AQ content. So AQ combinedly will be shift left side. So once we are going to shift left side, left means like that. So we are going to make it, this one will be here. Similarly, this bit will come out to here, and here this one we will be deciding based on the algorithm that says. So we will come across that, like how this bit is basically going to decide. So once we will be first shifting the left by 1 bit. So once we are going to shift it, so up to here, so we will just write it. So we need to shift it this way. So once we are shifting it here, so that will be 0, 0, 0, and this 0 will come out here, and then 1, 1, 1, and there will be a bit here. But that what that will be bit will be, that will be decided further. So once we have just done the shifting. So once we have done the shifting, after doing the shifting, left shift AQ, now we need to do A minus M. So we need to do A minus M. So accumulator is 0, 0, 0, 0, because accumulator is 0, 0, 0, 0. Okay. So now we need to do the M. We need to subtract the M. So M value is 0, 0, 1, 1. We need to subtract. Or if this is the M, we need to find out minus M. This is M. We need to find out minus M. If we want to find out M minus M, we need to take the 2's complement. So once we are going to take the 2's complement, it will be 1, 0, 1, 0, 1, 1. So this will be the 2's complement of minus M will be this value. So instead of doing this subtraction, what we can do is we can add 0, 0, 0 with 1, 1, 0, 1. So once we add it, it will be coming out like 1, 0 is 0, 1 is 1, 1 is 1. So this will be obtained accumulator. Okay. So in accumulator, this value will be there. Okay. Now once this is the value, we need to check this step. So either A is less than 0 or not. So here, because the sign bit is 1 into the accumulator content, so it is a negative number. It is a negative number. So that means A is less than 0. So this condition is satisfied, means it is yes. So once it is satisfying, the flow will be moving this way. So once it is moving this way, it is going to make like the Q0. So this is the Q bit. So Q0 will be this one, this bit. So once we have done the shifting, so the question mark bit will be stored as 0. This, once the execution moves to this way, the Q0 bit should be equals to 0. So instead of here, we should be making the Q0 bit is equals to 0. So we should further, and this is 1, 1, 1, and there is, at that time the accumulator content is this one. So accumulator content is 1, 1, 0, 1. So this is, we have done the shifting first, and then we have done the A is equals to A minus M, and now once we have checked it, it is going in this way. So we are going to make the Q0 bit as 0, and now at the same time we need to make A plus M. So once Q0 bit is, as we have done the A minus M, now we need to do A plus M. So we need to do A plus M. So A is this one. We need to make addition of 0, 0, 1, 1. So 0, 0, 1, 1. So once we will be doing the addition, it is 1, 1 is 0. A carry 1, 1 is 0. A carry 1, 1 is 0. A carry 1, 1 is 0. A carry. So we will be ignoring this carry. So now the A content should be this. So this should be the content of A 0, 0, 0. And we need to move the next. Now the count is 4, but now it should be count minus 1. So we should be reducing the count value by 1. So here the count has now 3. So once it is reduced to 3, we should be moving here and we should be checking whether the count value is 0 or not. So if count value is 0, we should be moving to end. Otherwise, we should be moving to no side. So as the count value is 3, it is going to no side because this condition is not satisfied. So it will be again going to here and go with the shifting. So now it will be doing the shifting of accumulator and Q value. Or so this was the accumulator and Q value. So now it will be moving the shifting left by 1 bit. So again, because between this step to this step, this is the, you can say, individual steps that is being performed. So that is not given. That's why I have made it. Okay. So in this case, here basically it is going to consider the case. Okay. So once we are moving to the second side, second loop, a second iteration, basically we should be moving the shifting. So once we do the shifting, it will be like 0 0 0, and this one should be shifted to here. Okay, and then 1 1, and there will be a question. So what this Q naught value will be there, that will be decided either this way or this way. So we should be, once we have done the shifting, now after doing the shifting, we should be checking the A minus M. So again we will be doing the A minus M. So again A is 0 0 0 0 only. Okay, but after doing the shifting, now the A value has become like 0 0 0 1. So once the 0 0 0 1 is there, this is the A now, and we need to subtract the M value. So or we are subtracting M value, or we are adding the minus M value. So minus M value is 1101. So 1101 will be adding. It is 1 and 1 is equals to 0 with a carry. Then after adding, it is 1. 1 and 1 is 1. 1, oh sorry, 1 and 0 is 1. 1 and 0 is 1. So this is the value of accumulator after adding, after subtracting. So it is 1 1 1 0, and this value will be 1 1 0 and question mark. But as this value is, new value of A is this one, here again the sign bit is 1. That means it is again a negative number. So when it is again a negative number, so once it is negative, that means A is less than 0. It is less than 0. Then S is satisfied. That means it is yes. So again it will be moving to this way. So once it is going to move to this bit where it is just like it should be deciding the Q naught value as 0. Okay, and then it will do again restoring. So once we do the restoring, it will be making A plus M. So doing A, this one solving the A plus M, the value, initial value should be there, that is 0 0 0 1 will be there, and the Q value will be like 1 1 0 0. This is after doing the addition, and this is left shift. Okay, so this is left shift and this is subtraction. This is subtraction and this is done by addition. So similarly we can put here also, the first step is left shift, this subtraction, and this one is because of addition. This addition is nothing but A plus M. Subtraction is A minus M. Left shift or shift is there, that is shifting the left side. And then again it will be reducing the count value by 1. So it is now reduced to 2. Once it is reduced to 0, taking the count value that it is 0 or not. So as it is not 0 because value is 2. So again it should be going into the loop. Okay, and then again do the left shift AQ. So again it should be doing the left shift AQ. AQ should be shifted left side. So once it is shifted left side, it will be 0 0 1, and this 1 will come here. Okay, and similarly you can see here also. So this one here, and here remaining is 1 0 0, and the Q naught bit will be decided later. So once we have obtained this, now we should be doing the A minus M. So again here A is 0, 0, 1, 1 minus M is 1, 1, 0, 1. We add, so this 1, 1 is 0 with a carry of. So now the A value is 0, 0, 0, 0. So once the A value is 0, 0, 0, 0, we can just see whether it is a negative number or not, or its sign bit is negative or not. So as it is 0, 0, 0, 0, its sign bit is not negative. It is, you can say, the positive number, because the sign bit is 0, it is a positive number. So once it is a positive number, it will not be going in this way, it is going in no side. So once it is going to no side, the Q value should be set Q naught value should be set to 1. So now it should be setting the value of Q naught as 1, 0, 0, and 1. So this will be the Q naught value. And now it should be moving to the count side. So why as it is going to move the count side, it is not going to perform addition on this number basically. Okay, so it is not going to perform the addition, means after subtraction, whatever the value is obtained, the value will remain the same. So this is like, after doing this, it is basically, once it is going this way, this is done after subtraction. And once we have done the subtraction, there is no need to do the addition now, because in this part there is no addition. So now we should be reducing the count value by 1. So this is the similar that is given here also, that is obtained. So now we should be making the count value reduction. So count value reduction will be doing from 2 to, it will be reducing to 1 now. So the count value is now 1. So once the count value is 1, again it is not 0. So it will be again moving to here and do the left shift of AQ. So A and Q, this is the same A and Q. So once we have done the A and Q, we should be shifting it left. So once we are going to shift it left, it is like 0, 0, 0, and this 1 will come out here. So it is 0, 0, 0, 1, and then it is 0, 0, 1, and there will be a question mark, like what should be the number. So again, after left shift, we should be moving the value of A as A minus M. So we should be doing A minus 1. So A is 0, 0, 0, 1, and minus 1 we need to perform. So minus M is 1, 1, 0, 1. So once we are going to add it, 1 and 1 is 0 with a carry. So this is 1 coming out here, 1 and 1. So this is the value of A after addition, after performing A minus 1 operation. A minus M we have performed, this is the value. But here you can see this is the negative sign indicating the negative value. Once it is a negative value, it should be went to this path. So once it is going to this path, it's going to make the Q naught value as 0. So here will be like 0, 0, 0, 1, and then the value should be like, the value of Q naught will be made to 0, 0, 1, and 0. Once this value is made, now we should be doing the addition operation. Okay, so once we have put the value of this, after that we should be doing the operation that is called the, yes, once we have done this, we need to perform the addition now. So once we will be doing the addition now, once we have done the addition, the value should be like, initially it was 0, 0, 0, so it will again come out to a 0, 0, 0 only. Okay, so once we are going to make it value, so after addition it will be 0, 0, 0, 0, and the Q value should be 0, 0, 1, 0. Okay, and then we should be coming out by reducing here. So once we reduce it, it is like the n value will be 0, the count value is 0. So now that is the end of the operation. Once this is the end of the operation, the result will be like stored into, so the result will be like stored into A and Q. So A and Q will be having the result. Once the A and Q is going to have the result, so because up to here, so answer should be like 0, 0, 0, 1 should be there. So we will just see, we need to do the left shift. Once we have done the, okay, we have done the left shift, this is coming out here, 0, 0, 0, 1 is there, and this Once we should be doing the subtraction. So it is like 0, 0, 0, 1. In that, we're going to add 1, 1, 0, 1. So 1, 1 is 0 with the carry, and then this is a negative number. So once it is a negative number, we should be doing here. So the q value q naught should be equals to 0. Once the q naught is equals to 0, we should be performing the restoring. So once we are going to add the value, 1, 1 is 1, 1, 1 is 1, 1 is 0, 0. With the carry. So how it is going to make like shift A and Q left with 1 bit, since A is greater than M, A should be it should be going to do the like. So just a minute. So here basically once we are performing this operation, we are going to check it. Once it is less than, so up to here, like up to this one, it is correct. We have got the same answer. In the next case also we have got the answer that is same. Okay. So this up to here, that is okay. So we'll just again do it. So why it is giving the incorrect answer? So so A value is this one, and this is the Q value. So once we start the next loop, we should be doing the left shift. So once we do the left shift, it is coming out like 0, 0, 0, and this 1 will become here. And then once we are shifting it here, it is 0, 0, 1. And what will be the Q naught value? We should be deciding later. So once we have done the left shift, now we should be doing A minus M. So A value is 0, 0, 0, 1, and M value is 1, 1, 0, 1. Sorry. Actually, we are subtracting here this M value. We need to subtract it. So M value we are subtracting means 1, 1, 0, 1. So we should be adding it. So that will be A minus M. So we need to perform A minus M. A value is 0, 0, 0, 1. After performing the A minus M, so for performing A minus M, we should be adding A value with minus M value. So once we add it, it is coming out to be like 1, and 1 is 0. And the carry, that is 1, and then 1, and so this will be the answer at this stage. So at this stage, it is 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0. So this is a negative number. So once it is a negative number, it is going in this way. So once it is going this way, Q naught should be made to 0. Q naught should be made to 0, and it is going to make A is equals to A plus M. So A value is this one, and it should be doing the restore value. So once it is going to make the restore value, okay. So once it is going to make the restore value, it is not like in the next case, once it is going in this way, it should not be making it. Q value is quotient, that is 2, and should be moving the A value also. So once we are going to add this to M value, okay, we need to add the M value. We are again adding this one. So we need to add the M value, that is 0, 0, 1, 0, 1, 1. 1 and 1, this is 1. 1 and 1 is 0 with the carry. 1 and 1 is 0 with the carry. 1 1 is 0 with the carry. Okay. So actually, instead of adding m at the second stage, we have added minus m. That's why there is an error. Up to here, that is okay. That is a negative number. So once we have done this, we have shifted in the last cycle. We have just shifted this left side. After shifting, the Q naught bit will be decided like either it is positive or negative. So once we have shifted, after shifting, we need to perform A minus M. So to perform A minus M, this is the A value and this is the minus M value, and this is A value. So once we add these two, it will be automatically going to give A minus M. So once we add this two value, it is coming out 1110. So 1110. So this indicates basically like 1110. This is a negative number. So once A is negative number, moving this way, Q naught should be decided at 0. So once we have decided the Q naught as 0, now we need to add M to A. So A value is 1110. 1110. In that we should be adding m, not minus m. We have done basically here we are going to add, we are adding minus m basically. So instead of that, we should be adding the m value is 0011. So once we add 0011, it should be going to give like 00101. So the answer will be like here, after adding 0001 will be the answer. So this will be obtained. So now once we have done this addition, now reducing the count value. The count value was 1. So once we have reduced the count value, it is become 0. So once the count value is 0, now we will be checking the count value. So if it is 0, we should be moving to yes side because it is 0 now. The count value has reduced to 0. So now it is going to move yes side. That means now the end of operation will be there. So once the end of operation is there, so whatever the value of Q is there and A is there, that will be deciding the result. So Q value, whatever the Q value is there, that will be considering the quotient value, and whatever the A value is there, that will be the remainder value. So here in the Q, it is 00110, that is equivalent to like 2, and this is in the A value, that is 0001, it is equivalent to 1. So this is the quotient and this is the remainder. So the result will be like Q is equal to this, A is equal to this. So the remainder will be like 1 and the quotient will be the 2. So after dividing 7 by 3, we will be getting 2 is to 1 by 3. That will be the answer. So yes, so that's all about the non-restoring type of algorithm for dividing the numbers, unsigned numbers basically, in case of a fixed point number system. So in that we have made a mistake. So while adding, you need to take care, like we need to add minus m or we need to add m. So you need to take care of that. So we were adding basically the minus m, that's why there was an error. So this was the basics of restoring type of algorithm. In case of the restoring type of algorithm, we have seen that. So next part we will see is the non-restoring type of algorithm. So in case of non-restoring type of algorithm also, the similar concept is there. We should be considering the cases, like how it is going to divide the numbers. So once we have done this algorithm, so we will also see like if we want to implement it with respect to an hardware, what would be the hardware that is requiring to implement this algorithm. So basically we were doing the shift. In mathematical terms, we can say like we are doing the we are performing basically shift operation, we are doing the subtraction, we are doing the addition. So for doing the shift, addition and subtraction, we are having an ALU. So if we talk about it in terms of hardware, it should be like we should be, suppose we want to implement this, so what hardwares we should be requiring. So for that, we should be requiring an ALU. Okay, so this is basically the ALU we represented. So modification is the ALU will be like So this is the LU. One input will be from this way, another input will be from this way. So the first input to this ALU will be the M value, that is divisor. Another value will be the input, that is A. Okay. So this is the divisor that needs to be subtracted again and again, and this divisor is going to be added to the accumulator or to be subtracted from the accumulator. So these operations are required to perform. Along with that, we were doing the shifting the q bits. Okay, so A and Q shifting we need to perform. Okay, and shifting to the left side, and also we should be deciding this Q naught value. So this is basically the Q naught value, and this Q naught value is basically decided by the by checking the content of accumulator, whether it is positive or negative. Okay, based on that, we will be deciding the Q value. So for this example, we have used 4-bit divisor and dividend. So basically, we will be requiring 4-bit of data bus, you can say 4-bit of data bus, and 4, because these are the 4-bit accumulator is there, 4-bit divisor is there, and also the Q, that is dividend, is of 4-bit. Okay, and once we have done the addition or subtraction, we have done this, we should be comparing it, because we are going to make whatever the result is there, we are going to make that result compare with the accumulator. We are going to check it, and after doing this subtraction or addition, we are performing addition or subtraction with M and A. So for that, an ALU is required, and after that, we should be moving to the A accumulator and doing the shifting between A and Q. So shifting left side we should be performing. So here an ALU is used, that should be of 4-bit addition and subtraction is should be performing. So in terms of hardware, we can say like these number of hardwares we should be requiring basically for implementing the division of 4-bit numbers. Similarly, in terms of other bits, suppose 5-bit is there, you should be requiring then 5-bit addition. We should be performing with 4-bit or 5-bit, whatever the requirement is there based on the numbers we have taken for an example. So the hardwares, so these are the hardware circuit basically for the division. Similarly, we can implement the hardware requirement in case of both algorithm also. So in case of both algorithm, you can just see what we were doing is here again we were doing the subtraction and the addition. Along with that, we were doing the shifting. So here shifting of A, Q and Q minus 1 bits are being done. So here also, if we talk about the hardware point of view, we should be having an accumulator that will basically perform the addition and subtraction. So addition and subtraction here also it is done with respect to A and M. So the first operand should be M, second operand will be the accumulator, and based on the content of like Q naught and Q minus 1, we should be deciding this either should be doing subtraction or multiplication. Okay, sorry, subtraction or addition basically. And also we were having here the right shift. Basically, we were doing the right shift, so we should be doing this arrow and that way. So A, Q and Q minus 1. So while shifting, we were doing like that. So we should be checking this shift operation. So in that case, we were going to take like this is the q0 is there and this is q minus 1 is there. So we were shifting a q naught q and q minus 1. We were shifting like that, and based on these bits we were deciding either performing addition or subtraction. And after doing the addition and subtraction, whatever the results were there, we were storing it into the accumulator itself. So we can think in that way, like how we were going to do the operations. So this is how we can say. So suppose in terms of here, the example we have taken is also a 4-bit. So here we can say like the data lines will be of 4-bit, and this is ALU. This will be a 4-bit. So 4-bit addition and subtractions are basically required in this case. So this is the in terms of hardware point of view. Next we will see is the non-restoring algorithm for division. So in case of non-restoring algorithm, we will make it. Yes. So this is the basic algorithm used for a non-restoring type of divisions basically. So here you can just see it's similar to all other algorithms. Here also we should be performing the operations like shifting left, shift, and addition and subtraction we are going to perform. And also we are checking whether the accumulator content is less than or equals to 0. So here basically the sign of the accumulator content is being used to decide either q naught value should be 0 value should be 1. And this is also doing this count reduction, and then going further, once the count is 0, at the end of the count is 0, we should be checking whether the accumulator content is 0 or less than or uh, greater than 0, that is positive or negative. Then also we should be performing an last operation, that is a plus m. This is basically non-restoring. So in case of here, once we are doing the addition or subtraction, we are not restoring the a value. At the last, we were adding m value to a. We are not checking in between. So we are not restoring. We are not using the restoring concept. That's why it is called non-restoring algorithm basically. So here we will be starting with, suppose we have taken an example of we take like, suppose we are going to do 11 divided by 3. If you want to do like that, so or you can just write it's like 11 by 3. So this 11 is, this is dividend and this is the divisor. Okay. So 11, that is in decimal. If we want to write it into binary, we can write in terms of binary as 8, 10 and 11. And similarly the 1 will be like 3 will be 0011. So this will be in case of the binary representation of 3 and 11. And this divisor should be stored into m. So the m value will be equals to the divisor, that is 0011. Similarly, the minus m value will be like its 2's complement. So its 2's complement is like 1011. So this is minus m. So this is m and this is minus m. Okay. So we will be starting with like initial value. So initializing this, basically we will be initializing. So count value or the n value we will be considering here is because whatever the number of bits are there into the divisor and dividend, that will be the n value. So here 4 is there, so it will be 4. Next, if we will be writing is the m value, that is the divisor. So divisor is here basically 0, 0, 1, 1. That will always be constant, the same. And then we will be checking the a value, the accumulator. So the accumulator is initially 0, 0, 0, 0. And then we will be going to check the q value. So q value is dividend. So dividend is this. So from here you can just write like q value is 1, 0, 1, 1. So q will be 1, 0, 1, 1. Okay, so this will the q value. And now what operations will be performed? We will be writing it. Operations we will be performing. Okay, so this is basically the initialization. So we can say this is the initial stage is there. This value will be there. So this is the algorithm. So we should be proceeding step by step into the algorithm. And with respect to that, what will be the changes into the different register content? We will be modifying one by one. So starting with like the first is we need to check the a content. So either it is 0 less than 0 or not, like it is a negative or not. So if it is a value, we should be checking. So initially the a value is 0, 0, 0, 0. So if it is 0, 0, 0, 0, this is not satisfied basically. So when it is not satisfied, it should be doing the no, because it is 0. So 0 is not less than 0. It is equal to 0. Okay. So it is like no, it is not satisfying this. So it should be moving into this direction. So once it is moving into this direction, then the first step is shift left accumulator and q. So accumulator and q we need to shift into left side. So we should be shifting to the left side. So this value will be like 0, 0, 0, and this 1 will come here. It will become like that. And then q value will be 0, 1, 1. So once it is 0, 1, 1, then this value will be deciding with the next step. So we will be doing this. So this is basically the left shift. Left shift we are going to make. So once we have made the left shift, now we need to perform the a plus a minus a is equals to a minus m. So once we need to perform a minus m, so a value is here now 0, 0, 0, 1. So this is the a value, and once we perform a minus 1, we can do like we can add a plus minus m. So minus m value is 1, 1, 0, 1. So 1, 1, 0, 1. So once it is equivalent to minus m. So once we add these two, it will be equivalent to a minus m. And we need to use this as a. So once we add it, it is 1 and 1 is 0 with a carry. 1 and 1 is 1. 1 and 0 is 1. 0 and 1 is 1 and 1. So this is the accumulator content. So after this step, the accumulator content is this. So we'll be writing it here. So 1, 1, 1, 0 is the accumulator content, and the q value will be like the same. So 0, 1, 1, and the question mark. Okay, because still the q not bit. So this bit is basically the q not bit. So q not bit is still not decided. So once we have done this, now after doing the subtraction, we will again be checking the content of a. So again the content of a is here, negative is there. So because there is a negative sign. This is sign bit is 1, so it is a negative number. So a is less than 0. So this is satisfied because it is less than 0, because it is a negative number. So it is less than 0. So it is satisfied. So yes side, we should be moving to yes side. Now yes side is saying like q naught bit should be equals to 0. So q naught bit should be equals to 0. So it is like 0, 1, 1, and then it comes out to be 0. So it says like, so at this stage we were making like A is equals to A minus M. At this stage we are going to make like Q naught should be equals to 0. 0 should be made to Q naught. And once this is 0, the A value is still, so after that we should be going to reduce the count. So now we need to reduce the count value. So count value is 4. Now the count value is 3. The count value is 3. So again we should be checking the value of count whether the count is 0 or not. So if it is not 0 because 3 is there, so we should be moving again to this step. So once we move to this step, again we should be checking the content of A accumulator content. So accumulator content we should be checking. So here once we check the accumulator content, we can say this is again the negative number. So if once it is negative number, it will be going to yes side. Okay, because it is a negative side. So once it is negative, it will be going to yes side, and then it will be doing the shift left AQ. Again, we should be doing the shift left AQ. So once we do the left shift, the content will be 1. I think it is not clearly visible. Okay, so we should be doing like 1 and then 1, 0, and this will be shifting here because we should be doing the left shift. Then 1, 1, 0, and there is a question mark. So this is basically the left shift. And now we need to do the A plus M. We should be doing the A plus M. So A value is now 1100, A value. And M value, we should be doing the addition. So M value is 0011. So 0011 is there. So once we do the addition, so this is 1111. So this is the A value. So after addition, this is the value. So A value after addition is 1111. This is done with A plus M. We have done the addition. And then the Q value will be remaining the same. Now we should be checking again the A value. So if again the A value is again the negative number, so it is less than 0. So once it is less than 0, we should be moving to this way. So again Q naught will be equals to 0. So the next step is A value will be same. The Q naught value will be 0 because this is going to say like it is 0. So we need to set Q naught to 0. And then we should be reducing the Q value. So once we are reducing the Q value, the next count value, the count value will be like 3 minus 1, that is 2. Now we should be moving to the next loop side, next iteration. So once we are going to have the next iteration, so in the next iteration again we should be checking the value of A. So again it is negative. So once it is negative, it is yes satisfied this way, left shift. So we should be doing the left shift. So it is going to have 1, 1, 1, and this 1 will come here. So it is 1. So this is 1, 0, 0, and this one. So the left shift is there, and this Q naught bit is not decided because once we are shifting left, we are not going to take this bit to that way because most significant bit will be discarded in the left shift, and the new bit will be directly like 0 pad. But this Q at the later stage, so that's why we have made it the question mark. Okay. Once we have done the left shift, now we need to do A plus M. So A value is this one. We need to do the M, addition of M, 0, 0, 1, 1. So once we do the addition, it is 1 and 1 is 0 with a carry. 1 and 1 is 0 plus 1 is 1 with a carry. 1 and 1 is 0 with a carry. 1 and 1 is 0 with a carry. So this carry is basically this A content will be 0, 0, 1, 0. So after doing the addition, the A content is 0, 0, 1, 0, and this will be remaining the same. So this is A is equals to A plus M. So up to here we have done. Okay. Now we should be again checking the content of A. So A, you can just see here, this is the 0 MS. The MSB bit is 0. That means this is the sign bit. Sign bit is 0. So once it is 0, once the sign bit is 0, so this is not satisfied. That means this is not satisfied, means it is going to move to the no side. So once it is a no side, the Q naught bit should be equals to 1. So it should be making like 1 0 0, Q naught bit should be 1. So it is going to make Q naught to be 1, and the A value will be the same, and then it should be going to count, reduce the count. So the count is 3, 2. Now after reduction it will be 1, and then we should be again moving to the next iteration. So again we should be checking for A content. So A content is positive, so this is not satisfied, so it will be moving to no side. So once it is moving to no side, again it will be doing the left shift. The left shifting will be done, so it is 0 1 0, and this will be coming here. So 1 0 0 1, there is a question mark, so this is left shift basically is done. Once doing the left shift, we should be moving the content of A as A minus M. So we should be doing the A minus M. So A is 0 1 0 1, and minus M is 1 1 0 1. 1 1 0 1. We should be adding it. So 1 and 1 is 0. There is a carry. So 1 1 1 0 0 is 1. 1 and 1 is 0 with the carry. 1 and 1 is 0 with the carry. So this the carry discarded. So the accumulator content is 0 0 1 0. So 0 0 1 0 is the accumulator content, and the Q value will be the same. So it is A is equals to A minus A is basically A minus M. So up to here, I think everyone got the point. So once we have done this part, now we should be again checking the A value. So A value is again the positive. So it is not satisfied. So it will be moving to no side. So once it is going to move to no side, there will be 0 0 1 0. Then Q naught value will be 1. So it is 0 0 1 1. This is Q naught value is 1. So once it is done, we should be going to reduce the count value. So count value is, instead of 1, now the count value should be 0. Once the count is reduced, the count value is 0. So once it is 0, we should not be going that way because it is satisfied now. So once it is satisfied, it should be going to the next side, like the yes side. So once going to the yes side, it should be checking the sign of A again. So A accumulator content sign is positive, so it is a positive number, so it is not less than 0. So A is less than 0, it is not satisfied. Once it is not satisfied, it will be moving to no side. So no side is end. So now the end will be there. So once it is end, the content of the accumulator. So here, once it is end, A is storing 0 0 1 0, and Q is storing 0 0 1 1. So you can just see, once we divide this 11 by 3, it will be going for 3 times, and 2 will be the remainder. So it will be equals to like 3 times it will be dividing. So 3 will be the quotient and 2 will be the remainder. Quotient value is this one. Its decimal equivalent is 3, and this is accumulator content is 0 0 1 0, that is equivalent to 2. That will be the remainder. This is the quotient value. So this is how the division in case of non-restoring type of algorithm works. So there is a basic difference between the restoring and non-restoring. So we were not using again subtraction and then addition in the same path. Here restoring concept was not implemented in case of this concept. Okay, so this is all about the basic of division algorithms. Okay, so now we will see the next part, that is floating point numbers. So that we will see Yes. So the floating point numbers we will see now. Up to now we have seen the fixed point numbers and their arithmetic operations, basically the addition, subtraction, multiplication, and division. Next we will see is the fixed floating point numbers. So before that, just a basics. So in terms of like uh, fractional numbers in binary, we represent is like there will be a decimal point. So in case of binary number system, this point is called binary point. Like in decimal, we were having like 11.56. So this point is called decimal point. In case of binary number, suppose 1101.0011 is there. So this point is called binary point in case of binary number system. This is the decimal number system. So similarly, this binary point is there, and left to this binary point is having the 2 to the power some value that will be resulting into a positive value, or it is having the positive powers of 2, and the right side to this binary point is going to give the negative powers of 2 in case of a representation of the fractional binary numbers. So binary numbers we have seen directly like 1101 is the binary number. This is the binary number. But if we are going to use the binary point, this there will be the number that will be called as the fractional binary numbers. So in this case of representation, we will see like how we can represent fractional binary numbers with float concept. Floating concept means this that is getting a fractional binary number is not fixed. If it is moved this way, then this is called the floating type of binary representation. So here the representation is bits to the right of binary point represents the fractional powers of 2, and in terms of the numbers you can represent it like that. So that we have already seen. So it's some examples we will see like 101.11 it is written. This is an example of binary points or binary numbers basically. Again, next number is there. It is also a binary number, that is a fractional binary number. This is another number. So that is going to represent the fractional binary number. And what is its equivalent? You can just see its equivalent in case of decimal is like 5. So this number is going to have 5, and this is the fractional number, that is 3/4. Okay, and similarly this number is 2 and 7/8. So you can write like it is 5 is to 3/4, and this one is the number that is 2 is to 7/8. Similarly, this number is 63/64. So this is how we can represent the binary numbers. So in case of representing a binary number, there are some most frequently used sign conventions will be there. It's like once we are going to divide by 2, once we want to divide by 2, we should be shifting the decimal point, or in case of binary numbers it will be like binary point. So we will be shifting this binary point to the right side, then the resulting number will be divided by 2. Similarly, if we want to multiply by a binary number, multiply a binary number by 2, then we should be shifting it to the left side. Okay. And also in terms of the observation, you can see like if it is 0.1111, that is in case of binary number system, then this will always be less than the 1 value. It will always be less than 1 value, because if it is 0.9999, it is in case of decimal, then this will always be like whatever the number will be there, that will always be less than the 1 value in decimal. Similarly, in case of binary, we can represent it like that. So this 0.1. So 0.1 is nothing but 1 by 2, and 0.01 is nothing but 1 by 4. Similarly, once we add it to here, it will be either less than, just below the 1 only. It will be less than the 1 value. In case of representation, the basic representation is there. The different representable numbers we will see and their limitations. So in case of limitations, we can say like here can only exactly represent the numbers of the form x by 2 to the power k. So in case of binary representation, in case of the fractional part, whatever the numbers we are going to represent, we should be able to represent exactly these numbers only, that will be having the powers of 2 in such that x divided by 2 to the power k in terms of fractional numbers. Okay. And other rational numbers have repeating bit representation. So other numbers will be having a repetition. So if we are able to use 1 by 2 or 1 by 4 or 1 by 8 is there, if any value is there in fractional, that is the part of, or that is constituting either this or this or this, then that can be having the non-repetitive representation basically. Okay. But in case of any value other than that will be there, that will be having like a repetitive value. So if it is 1 by 3, you can just see like it is not going to stop. It should be having the value that is repeating till infinity. So it is 0 1 0 1 0 1. So 0 1 is repeating here. So 1 by 5 is there because this is 1 by 4. That once we want to represent 1 by 4, it will be 0.001. It is non-repetitive. Again 1 by 2 is there. So it is like it will be coming out when we are going to represent 1 by 2, it is 0.1 in decimal, in binary. Similarly 1 by 4 is 0.01, 1 by 8 0.001. So like that. So it is having a non-repetitive pattern. But in case of other than these combinations, if any number is there, 1 by 3, 1 by 4, 1 by 10, then it will be having a repetitive pattern. It will keep on repeating again and again. So this is the basic limitation to the binary representation. That's why we should be moving to the new representation that is called the floating point representation. So before these, whatever the numbers we have seen, these are like the fixed point numbers. So in terms of fixed point numbers, we should be using the decimal value, that is, or the binary point that will be a fixed, will be there. So in terms of like representation, if we are going to represent in case of like 8-bit number system, there will be having the combination like this decimal point, or the this a binary number system, this will be the binary point. So this binary point is changing. If binary points are changing, then that representation will be called the floating point representations. So in case of fixed point numbers, we are going to use, like in case of floats are there, that basically use the 32 bits. If a double is there, then it will be using the 64 bit representations basically. So here, in case of like once we are going to represent the binary fractional binary numbers by picking a fixed place for an implied binary point, then it will be called that fixed point binary numbers. But if these binary points are not fixed, either the binary points are placed here or the binary points are placed here, so it is having the change in binary points. So these change in binary points representation are there. So the same number represented by this also and this also, but there will be a difference in what? So there will be a difference in range value, and there will be a difference in precision value. So based on this binary uh, point positions, there will be a decision of range. So if we are going to use like this, we are going to make this binary point between 2 and 3, then between 2 and 3, then we will be able to identify a certain range of values through this representation. Or if we are making this binary point between 4 and 5, bit 4 and 5, then there is a certain bit of certain values that can only be represented by this representation. So once we are going to take this binary value or binary point between 2 and 3, it is having the representation like it is having uh, this 5 bits for representing the range value, because once it is 5 bits, it will be like 2 to the power 5 will be the maximum value that can be represented in positive side. Similarly, if it is only 3 bits are there, it will be representing 2 to the power 3 only. So up to 8. This is up to 32. So the range here is going to change with respect to this binary point. Similarly, in case of precision we are talking about, so if after the binary point we are having only 3 bits, so this will be having the less precision. So it's like suppose in case of decimal number system, if someone is writing 10.987654, this is the number. Another one is writing 10.9 only. So which one is having the higher precision? So in both the cases, this number is having the higher precision. That means up to this much of bit, it is at this much of digits, it is able to accurately tell the value. But in this only, it is also 10.9 only, but it is having less precision. So it is having so much of error. So once we are extending the bits after this binary point, that will be giving out like how much precision. Once it is 2 to the power 3, then it is 8, so it is having less range, but higher precision is there. So the representation in case of floating point representation will be having the effect on the range value and also on the precision value. So okay, so next part we will see into the next class. Okay, so we will be starting with the floating point representation into the next class. So till then you can just go through the topics. So thank you.